Okay, now we are looking at the graph of successive IEs of the same atom X. So take note that this is different from what we did just now. Just now we were comparing the first IEs of different atoms. Now we are looking at the same atom, okay, but it's some successive IEs. Okay, that means the first, second, third IE of the same atom X. Okay, first, second, third, fourth, and so on. Okay, so you are given this graph for question 11. Okay, so there are a few things you need to appreciate regarding this graph. So the first thing is its general trend. Okay, so why in general the second IE is higher than the first IE, the third IE in turn is higher than second IE, and so on. Okay, so that will be part A. So the answer to that is because attraction between leaving electron and ion of increasing positive charge becomes stronger. Okay, what do I mean by that? So let's say for first IE, essentially you are removing electron from a neutral atom. Okay, then for the second IE, notice that you are removing an electron from a +1 ion. Okay, this +1 ion is positively charged. So there will be attraction between the leaving electron and this +1 ion. So it's this extra attraction, okay, that causes the second IE to be higher than the first IE. Then when we come to the third IE, now okay, we are removing electron from the +2 ion. So now this positive ion has an even higher charge. So the attraction between the leaving electron and this +2 ion is even higher than before. So the third IE is even higher, okay, and so on and so forth. So that's for explaining the general trend. Okay, but there are some increase that are larger than expected. So for example, if you look at the graph, okay, you should notice that there's this very big jump from the 5th to the 6th electron. Okay, so this big jump is larger than expected. It cannot be explained by what we said just now. It's actually due to a change in the quantum shell. Okay, so in other words, these 5 electrons, they are being removed from the outermost shell. But from the 6th electron onwards, it comes from an inner shell. Okay, so the electron in an inner shell is much closer to the nucleus, so requires more energy to remove. So that's why you see this very big jump. So when you see this very big jump, it tells you that there is a change in the quantum shell. Okay, so that's the answer for part C. The energy difference between the 5th and 6th electrons is much larger than usual. It's because of a change in the quantum shell. So this fact is very useful because it helps us to determine the group of element X. So as I said just now, okay, the first 5 electrons are in the outermost shell. So that means X has 5 valence electrons. So this will tell you that X belongs to group 5. Okay, then the electron arrangement in the outer shell will simply be S2P3, making use of the rules for writing electronic configuration that we have gone through before. So notice that I use N to represent the quantum shell because really I do not know whether the outermost quantum shell is it the 2nd, 3rd, 4th or whatever. So I just use N to represent. Okay, next, why can't X be nitrogen? If you look at the graph, okay, you notice that the question gives you the first 8 ionization energies of X. Okay, meaning to say that X must have at least 8 electrons. Okay, but if you check the periodic table, you will find that nitrogen only has 7 electrons, and therefore X cannot be nitrogen. Okay, so even though nitrogen is in group 5, X cannot be nitrogen, but it can be phosphorus and the other elements that are below phosphorus in group 5. Okay, next you are asked, why is the energy difference between the removal of the third and fourth electrons slightly different, slightly bigger compared to the second and third electrons? Okay, so the question is referring to this part here. So this is what I call a small jump, meaning to say that it's larger than the other normal increases, but is smaller than this big jump here. Okay, so the increase here is slightly larger than expected. So this sort of small jump will be due to a change in the subshell. Okay, so remember we said that the 5 valence electrons are arranged in this way according to this electronic configuration. Okay, then remember electrons are always removed from the outermost shell. Okay, so the first electrons to be removed will be from the p subshell. Okay, so can you see that the first 3 electrons actually corresponds to electrons from the p subshell. Then from the 4th electron onwards is removed from the s subshell. So between the 3rd and 4th electron, there is a change in subshell from p to s. So that's why there's a small jump. Okay, so the answer is here. The 3rd and 4th electrons are removed from different subshell. Okay, there's a change from p subshell to s subshell. So that's why there's a small jump. So for this graph, you need to understand 3 things. Okay, 1, the general trend. Why is there a general increase? Then secondly, the big jump due to change in quantum shell, and a small jump due to change in subshell. Okay, finally we look at question 10. This is also related to what we explained just now. It's similar, okay, except that for question 11, they give you the data in graphical form. Okay, but here the data is given to you in numerical form. So what could be the formula of the chloride of Z? Okay, so first you need to find out the group number of element Z. So that means you need to locate where the big jump in ionization energy is. Okay, so that means you have to work out the difference, okay, between every 2 successive IEs. So by that I mean the difference between these 2. Okay, then the difference between the next 2, and so on. Okay, then you should be able to see that the largest difference occurs around here, from 5th to 6th. The difference is around 6,300. Okay, definitely much larger than the other differences. So this means that there's a change in quantum shell. Okay, so that means from the 6 electrons onwards is being removed from the inner quantum shell. So this will tell you that the first 5 electrons are in the valence shell. In other words, Z is in group 5. Okay, so you know that a group 5 element can therefore form a chloride of this formula ZCl3. Okay, it gains 3 more electrons to form the stable octet configuration. Okay, so that's all for atomic structure tutorial.